Hello everyone and welcome to this online tech talk on encrypting Amazon ECR images with AWS KMS. My name is Pavan Mistry and I'm a senior developer advocate with the AWS Container Services team. I worked in AWS previously as a specialist solutions architect and as a manager within AWS Security and Compliance. Prior to AWS, I worked as a security consulting leader at global enterprises. You have my email address and Twitter handle on this slide, so feel free to contact me through email or Twitter anytime for any questions on AWS Container Services, container security, or AWS security in general. This is a level 300 tech talk, so understanding of AWS and Amazon ECR is expected. First, for context, we'll quickly understand the fundamentals around Amazon ECR and AWS KMS. Next, we'll do a deep dive into how KMS encryption works with Amazon ECR. And at the end, we'll use this feature in action to build a transaction microservice using AWS Fargate that meets a set of security and compliance requirements. I have a demo to accompany each of these topics as well. The goal of the tech talk is to leave you with an understanding of securing Amazon ECR and how AWS KMS can help. This will help you make an informed decision to secure your repository images at rest and meet regulatory and compliance requirements for your Amazon ECR container images. We'll end the tech talk with a Q&A session. So before we get started and actually dive in, we are making some assumptions. One, that there is a high-level understanding of Docker and containers in general, specifically what a Docker container image is and how to work with container images and so on and so forth. We also assume a basic understanding of working with AWS Console and AWS services like Amazon S3. In particular, we'll be talking about issue number 52, which is on the screen from our AWS container roadmap on GitHub, which was closed at the end of July when we launched AWS KMS integration within Amazon ECR. To accompany the AWS KMS integration, AWS's Amazon ECR engineer, Lahiru Disaniake, and I wrote a blog post to announce or introduce and walk through this feature. So with that, let's talk about Amazon ECR. Amazon Elastic Container Registry, or Amazon ECR, is a managed AWS container image registry service that is secure, scalable, and reliable. Amazon ECR supports private container image repositories with resource-based permissions using AWS IAM so that specific users or Amazon EC2 instances can access repositories and images. Developers can use their preferred CLI to push, pull, and manage Docker images, Open Container Initiatives or OCI images, and OCI-compatible artifacts. Amazon ECR is integrated with the AWS ecosystem with services such as AWS Elastic Container Service or ECS, Elastic Kubernetes Service or EKS, Identity and Access Management, and our Key Management Service. An example of integration will be with Amazon ECS. By simply pointing the image to the image in ECR, ECS will retrieve the appropriate image on your behalf. Amazon ECR stores its images in Amazon S3, which means it inherits the high availability and durability that you get from Amazon S3. ECR also secures your images by encrypting them at rest using AWS Key Management Service or KMS, as well as in transit by using HTTPS. And ECR also integrates with AWS Container Competency Partners. Lastly, Amazon ECR eliminates the need to operate your own container repository infrastructure by letting AWS handle the undifferentiated heavy lifting. So when you think about managing your own container repository, the front end, the storage backend, security and compliance, that's what we call the undifferentiated heavy lifting that AWS handles. So this brings us to discuss the security and compliance benefits that the AWS KMS integrations brings to our Amazon ECR customers to take away the undifferentiated heavy lifting. To understand this, we need to understand some fundamentals around container image and layers. So Docker containers are building blocks for applications, and each container is an image with a readable or writable layer on top of a bunch of read-only layers. These layers, also called intermediate images, are generated when the commands in the Docker file are executed during the Docker image build. For example, here's a Docker file on the screen for creating a Node.js app image, and it shows the commands that are executed to create the image. Once the image is built, you can view all the layers that make up the image with the Docker history command, which is also shown on the screen. So let's take a look at a quick demo to get hands-on with this. Right, so on the terminal, I'm going to look at my repositories within my account, and right now there aren't any. We'll also take a quick look at the console, and that reflects the current status of no repositories. Now I'm going to create a repository and name it Nginx as a sample. It has default encryption, which is AES 256. The scan on push feature is disabled, and this is a repository URI. So now I'm going to look at the images on my local machine through that command, Docker container ls and ps. We don't have anything on the local machine right now. So what I'm going to do is pull an image from Docker Hub, which is available publicly. And here you can see that the layers are being pulled and the pull is complete. So when I do Docker images, you can see that it's on my local machine with an image ID. Now, if I do a Docker history to that image ID, I can see all the commands which built up this image and when it was created, and all the details along with the layers that make up this image. This is important to understand because it helps understand the way the encryption has been implemented. Now I'm going to tag my image and also then push it to the new repository that I have created in my account. So you'll just quickly change the name, the tag, and push it out. As you can see that there are layers being pushed up to my ECR repository that I created with the default encryption AES 256. So if you want to log in, so you need to authenticate with ECR, and that's the command you can use. Now we'll quickly look at the repositories, which is the one that we created, Nginx, and then we'll look at the images within that repository, and we should be able to find one image being pushed within there, and also we'll verify that on the console. And here you can see that we have the URI and the image tag, which is latest, which was pushed within ECR. So we looked at how to set up a repository and add images to it with the default server-side SSE S3 encryption using the AES-256 algorithm. We learned from several customers that to meet your security and compliance baselines, you wanted to use AWS KMS to benefit from AWS managed or customer managed CMKs or customer master keys that you created or owned to encrypt images in Amazon ECR at rest. Some customers prefer the audit, access control, and monitoring features using these keys with control over key material origin. With the KMS CMK integration, customers now have the ability to select key material origin for their CMKs from KMS, whether it's external provider, custom key store using CloudHSM, or KMS HSM. We'll look at these options in a demo later in this tech talk, and this is what we have implemented through the July feature launch. So in this graphic from the blog, we can see that a repository can consist of multiple images, and each image consists of layers and manifest. For more control over the encryption for your Amazon ECR repositories, you can now use server-side encryption with customer master keys stored in AWS KMS. So when you use AWS KMS to encrypt your data, you can either use a default AWS managed CMK, which is managed by Amazon ECR, or specify your own CMK, also referred to as customer master key, customer managed CMK, stored within AWS KMS or CloudHSM. So the CMK is used to generate and encrypt and decrypt data encryption keys, as you can see on the screen, within each layer, that are then used to encrypt the layer and manifest. In the previous demo, you may have noticed that we created a repository without providing any KMS parameters using the AWS CLI. This created the repository with the default SSE S3 or server-side encryption with S3, which uses the industry-accepted AES 256 encryption algorithm. With the new feature, customers can pass additional KMS configuration to use either the AWS managed KMS key or create their own CMK in KMS and specify it whilst creating the repository as shown on the screen. But before we take a look at this in action, we need to understand envelope encryption and AWS KMS and the benefit this provides to our customers. So let's take a look into this. So this is a visual representation of envelope encryption fundamentals. Envelope encryption stores the encrypted data key and the ciphertext of the data together. That is represented in this diagram on the right. In AWS KMS, the master key is referred as customer master key and is also referred to as key encryption key or KEK in some places. Understanding envelope encryption is important here because the encrypted data key, also referred to as data encryption key, generated using the CMK or the master key, is stored with each encrypted image layer as we saw in the block graphic. And this data key is unique for each layer. And that's a very important feature to understand. Now let's take a look at the key management service as it encrypts and decrypts the data encryption key using the CMK. AWS KMS provides a web interface to generate and manage cryptographic keys and operate as a cryptographic service provider for protecting data. AWS KMS offers traditional key management services integrated with AWS services to provide a consistent view of customers' key across AWS with centralized management and auditing. AWS KMS is a secure and resilient service that uses hardware security modules or HSMs that have been validated under FIPS 140-2 to protect your keys. AWS KMS is integrated with services like AWS CloudTrail to provide you with logs of all key usage to help you meet your regulatory and compliance needs. You can establish your own HSM-based cryptographic hierarchy under keys that you manage as customer master keys. These keys are made available only on the HSMs for the necessary cycles needed to process your cryptographic request. You can create multiple CMKs, each represented by its key ID. You can define access controls on who can manage and or use CMKs by creating a policy that is attached to the key. This allows you to define application-specific uses for your keys for each API operation. I recommend you to take a look at KMS Cryptographic Details white paper that is available for free, and the link is at the end of the presentation. So KMS has 3 key origin alternatives that helps meet Amazon EKS customers' key management requirements for secrets encryption. You may use the external or bring your own key option if your organization wants to control how your key was generated from certain entropy sources, and keep your own backup copy of your key material and upload keys only when you need them. The next option for key origin is AWS CloudHSM. CloudHSM is a cloud-based hardware security module that enables you to easily generate and use your own encryption keys on AWS. With CloudHSM, you can manage your own encryption keys using FIPS 140-2 Level 3 validated HSMs, and CloudHSM offers you the flexibility to integrate with your applications using industry standard APIs such as PKCS11, Java Cryptography Extensions or JCE, and Microsoft CryptoNG libraries. CloudHSM is standards compliant and enables you to export all of your keys to most other commercially available HSMs subject to your configurations. It also enables you to scale quickly by adding and removing HSM capacity on demand with no upfront costs. You might use the CloudHSM Key Origin option if your organization has requirements for key materials to be not stored in a shared environment, if it requires to be backed up in multiple AWS regions, or it must be subject to a secondary independent audit path and must be certified at FIPS 140-2 Level 3. Lastly, the last option and frequently used is if your Amazon ECR images require encryption using keys that are stored in a FIPS 140-2 validated HSM at overall level 2, then AWS KMS HSM helps you meet the requirement, which is kind of the default KMS HSM, which is where the CMK is stored. So this brings us back to take a quick look at FIPS 140-2, as I mentioned a couple of times for the validation for KMS and CloudHSMs. The links to the public FIPS 140-2 documents for both KMS and CloudHSM are available publicly. So if you can't find it, just message me and I'll be glad to help. Why would you use AWS KMS for encrypting Amazon ECR images? First, to meet regulatory, security, and compliance requirements for workloads using Amazon ECR repositories. Second, you may want to use alternatives to meet your requirements for key origin as described previously, and also to manage key operational lifecycle expected from a service like AWS KMS. All right, so this brings us to a deep dive into the demo. So let's see these KMS key origins in action on the console this time. So here we are at the console and we have the repository that we created. But when I click create repository, I'm going to use a name which we'll use in the next demo. But here we can see that the image scanning is disabled. But this is a new set of options introduced with the new feature encryption settings. If we enable it, then by default, it will use the AWS managed key in your account, which is specific to ECR. Now, if you click on the customize encryption settings checkbox, it opens up an input box where it pulls in all your keys from AWS KMS for that account within that region. So here we can see that I have a few keys, and this one, Tech Talk KMS HSM, when I click on the key, it brings us to the KMS console and look at the cryptographic configuration. We can see that the origin is AWS KMS, which means that our CMK is being stored within the KMS HSM. Now I can pick another key if I would like, and in this case, this is the CloudHSM key, or the custom key store, which uses custom key stores, where you can see the origin is AWS CloudHSM, and this means that the CMK is being stored within the HSM cluster or the CloudHSM cluster. We can see there are two HSMs here, which is the minimum needed to build a cluster for custom key store, and we have two active HSMs with backups being taken regularly every day. So this is a quick overview around customer managed CMKs, and I'd go ahead and create this repository because that's the one I want. So I have created a repository with a CloudHSM CMK, Now, to use another example, I'm going to use AWS managed CMK in this case, where you do not need to specify a CMK yourself. AWS creates that for you. So now when I click on this repository, AWS managed CMK is being used, which means if I look at the key management service or KMS and take a look at AWS managed keys, I should find an entry for AWS ECR. So there you go. So ECR, this is an AWS managed key where the origin is AWS KMS, but the management is done by AWS. So the customers don't have to do anything around the management of this CMK. All right, I'm not going to use this, so I'll delete it, delete the repository. But this gives an overview around how to use the different options in KMS. Okay, so let's look at another demo which is more relevant, which brings a few things together for you. So here we're looking at building a transaction microservice, and before we dive into the actual demo, in a typical organization, provided security is baked in from the start and you've had an architectural review with security, there could be some specific security and compliance expectations to meet whilst building a microservice. In this notional example, we provide a security and compliance requirement set for a possible financial services or healthcare organization handling sensitive data like payment card data or patients' personally identifiable information. So the requirements to build this particular service that accepts input of the sensitive data, processes it, and provides an output are listed on the screen, where the service that you're creating or the developers are creating must be hosted on a PCI DSS and HIPAA compliant infrastructure. It must use ephemeral container storage that is encrypted during runtime, and it has the images encrypted when they are stored at rest with control over encryption master key lifecycle. So if these are the requirements put forward to you by your security team due to compliance or regulatory requirements and security baselines, then this is just an example which takes you through that process and helps you build on a platform that meets these requirements. So let's jump into the demo. So here I have a Docker file and app, which really is a simple app which takes in any input and provides a transaction processed or transaction failed output. And the Docker file is again just used to build this app and expose it on port 3000. So when I build this image, I'm going to use the transaction app, the repository that we created, and add a tag to it, 1.0, and build it. So here we can just see that it's pulling the required node images or layers and installing the necessary packages and also pulling in the details. Now it's built the image and tagged it. So within my image repository, you can see the app. This is local Docker images, and the next thing we do is to tag it to our ECR repository so that we can push it. So I'm going to do that now. So I've pasted the image, and now I'm going to push that image up to ECR in that particular repository, which has the CloudHSM CMK. So each layer which is being pushed is encrypted using the CloudHSM CMK, the data encryption keys generated through the CloudHSM CMK. So I'm going to make a minor change here where I'm adding logs to the console so that we can see those in CloudTrail. And we will just change the tag on the image and build a new image with a tag around logging. So I'm just going to add a new console.log tag to it so that I know that this image has logs built in. Now that I have the new image locally, I'm going to push it. Look at the images locally, take the image ID and push it out to my repository. So what that will do is it will add encryption to the necessary additional layers which have been added to this repository, and each layer will have the data encryption key generated and encrypted by the CMK, which is stored in CloudHSM. So now that I push this new image and the tag, so the new layer which has been pushed has a new data encryption key, and it's encrypted using that key. But the layers that exist have been previously encrypted anyway. So it meets one of the requirements that security and compliance have given to us around encryption at rest. So now you can see that there are two image tags. One is latest and one is console.log, and they're all encrypted using CloudHSM, which meets your key origin requirements as well. So I need to test the image locally just to see what it does, just to demonstrate what it does. So I'm going to run it locally, and so that I can test it and demonstrate what it does. But essentially, when I do a curl and send some information out to the service, to the microservice, like in this case, a card number, expiry date, and the CVC number, I should get an accept or reject, as in the transaction failed or transaction passed or cleared. So it's again a simple example where it's a service that processes data information. In this case, there is nothing happening actually, but you get a result out or an output after the processing. Assuming it processes personally identifiable or sensitive data, there are some security requirements attached to it. So now we'll use this image and create a Fargate task definition using Fargate platform version 1.4. The reason we would do that is we announced a feature of ephemeral storage encryption using AWS managed keys for Fargate. So I'm going to add container to this. We're going to use the same container which has the console logs attached to it. So that's the tag we'll use. Expose 3000, which is the port we expose, and keep the other defaults within this task definition. We'll use the CloudWatch logs to look at the console logs, and then so once we have that created for us, we'll create a service out of this, and when we create the service, we'll use Fargate and specify version 1.4. This is important because that's the platform version in Fargate that uses ephemeral storage encryption. So when we are running the container, the storage where the container is being run is encrypted using KMS managed keys or AWS managed keys. And we are just enabling access using modification to the security group here. Port range 3000. I'm going to expose it, and just for testing purposes from anywhere, so that I can test it. So next step is just to keep the defaults and create this service. And now that service is built, it's going to pull or provision it by pulling the image from our ECR. And as you can see, it uses platform version 1.4. And soon it will run the service. We have the public IP now, so we can use that to test it within our CLI. So now that it's running, I can go back to my CLI and then do the same thing again, and I should be able to run a few tests to see the output. So here I have processed successfully, so a couple of transactions that processed successfully and one more, and that's failed. So I can see that it's working. So we have a service up and running which takes in transactions, and just to see the integration with CloudWatch logs, you can see that those success transaction and one failed transaction is also appearing on the logs. So this is a quick demo which hopefully sort of showed you how to build upon the requirements, where one of the requirements is service must be hosted on PCI and HIPAA compliant infrastructure. So when we use ECS and when you use Fargate with ECS, that is a PCI and HIPAA compliant infrastructure. You can access the reports, the audit reports, through AWS Artifact. And the second requirement, ephemeral container storage during runtime, is enabled through Fargate PV version 1.4. And the third one is through the images where when stored must be encrypted at rest. So in this case, we used CloudHSM as the CMK store and key origin. So that is enabled through the ECR repository. So that was a quick example where you had a microservice up and running in just a few minutes, which meets all those requirements. So one more thing in terms of the feature documentation linked at the end of this tech talk is that there is a permission or a policy to take care for the CMK lifecycle. And when the AWS managed CMK for Amazon ECR is used to encrypt the repository, any principal that has permission to create a repository can also enable AWS KMS encryption on the repository. However, the IAM principal that deletes the repository must have the KMS retire grant, as you can see on the screen. So that permission should be enabled. This enables the retirement of the grants that were added to the AWS KMS key when the repository was created. So there are a couple of things to bear in mind which are listed in our documentation with the link shown on the screen. So that's something to take care of. But to wrap up and recap, we understood Amazon ECR repositories and images. We dived deep into the KMS integration feature with Amazon ECR. We looked at the benefits of encrypting images using AWS KMS and the available alternatives within KMS on where to store the CMK or the customer master key. And we created a sample microservice application which meets a certain security and compliance requirements within a few minutes. So there are a couple of recent feature updates which are interesting to Amazon ECR. So here's the link to multi-architecture container images for ECR and OCI artifact support in Amazon ECR as well. So there are a couple of interesting launches which we recently wrote about. And here's a list to getting started. So a few links which I mentioned during my presentation, and hopefully this was useful. So I'll close and thank you for attending this tech talk, and we'll open up to Q&A. So thank you very much.